All right, this is Math 189, Section 8.8, Example 1. All right, so we're talking about recursive sets. All right, this is what the induction that we've been doing is all about. All right, we're trying to get to this point where we're ready to do the work that's coming up next in Section 8.9, structural induction. Structural induction is all about induction on recursively defined sets. So you've really got to understand this section to understand 8.9. That's what it's all about. That's what we've been building to all semester. Okay, so first example. Let's see. So we're going to define the set S. So S for set, a set S, as follows. Okay, we're going to give a recursive definition for this set. Okay, the initial case. Okay, this is what the Xi book calls the base case. Now, I feel like this is the worst possible thing to call it because we already have a base case. Base case is for induction. I don't know why they would call two very important things that are kind of not really the same thing. So when you're looking through the Xi book at the examples, again, for the reading, or when you're thinking about what you read, think of it when I write initial case, I mean the base case for a recursively defined set. All right, the initial case, or the base case as they call it, is just the thing that gets things started. Okay, so the initial case is that let's say 0 is in S. All right, and now the recursive rule. Okay, so if n is in S, then n plus 2 is in S. You're going to go like this, so you think of it as one whole piece is in S. Okay, so the question now is, what common set is the set S? All right, so by common set, I mean there's another way that we really don't need to define S in this way. This is kind of a silly way to define this set S. But we always start, our first examples are kind of silly examples because we can see that they're true without having to use this new method of recursively defining the set, okay? So let's think about what set this is. Okay, now I'm gonna restate these things, just rewrite this stuff up here so we don't forget what we're doing. Okay, so the initial case is that 0 is in S, and the recursive rule. Okay, I'll often do that. I'll often write this as just as RR for recursive rule. Okay, recursive rule is that if n is in S, then n plus 2 is in S. All right, now because we're defining it with this recursive rule, we don't have to really say where n lives, right? So we don't have to quantify. We don't have to say, where does n live? All we're doing is saying, okay, we start off with 0, and then since 0 is in S, 0 plus 2 will be in S. Okay? All right. All right, so let's start with that. Now I'll often do something like this. I'll write S, and then I'm gonna sort of map out how S is created using the initial case and the recursive rule. All right, and so we'll think of on the board here is the set S, or at least a piece of it, because it's going to be an infinite set. And most of these recursive sets that you'll deal with are infinite. Okay, so it's going to be an infinite set here. And the thing to keep in mind, a good thing to keep in mind, just a concept, is that even though we can think of it as happening in stages, right? The initial stage, the first stage, is that 0 is here. So let's maybe think of it as stage 1, we have 0 as an S. Okay. And then the second stage would be to apply the recursive rule. Let's say we apply the recursive rule to that, right? Okay, so 0 is in S. If 0 is in so 0 is in S, all right? Now the recursive rule just says if something's in there, then that thing plus 2 is in there. So that says that 0 plus 2 is in there, otherwise known as 2, right? So that says that 2 is in there. 2 is in S. Okay, 2 is in S, so applying the recursive rule again, we see that 2 plus 2, which is 4, is in S. Okay, now I'm going to keep doing this for a little bit, and we're going to see what S is. You might already see exactly what it is, but the main point that I want you to get from this conceptually is that even though we think of it in stages, like this is the first stage gives us 0, or the first iteration, kind of like a loop, right? A for loop that goes on forever would crash your system, right? In math, the system never gets crashed, okay? All right, so it just goes on forever, and we're allowed to have these infinite things. Okay. All right, so even though we're thinking of it in stages, stage 0, stage 1, stage 2, stage 3, stage 4, to a mathematician, and how you should think of it is this: once we give these rules, the entire infinite set is created at once. Right? Even though we think of it in stages, it actually just happens like that. Okay? At once. And yes, I like snapping my fingers. Okay. All right, so the initial case gives us 0. We apply the recursive rule once, and we get 0 plus 2 is in there. Apply the recursive rule again, we get that 2 plus 2 is in there. Apply the recursive rule again, we get that 4 plus 2, or 6 is in there. Apply the recursive rule again, we get that 6 plus 2, or 8 is in there. Right. Okay, and just keep doing that forever. Right. Okay. Right, so do you see what S is? Okay. All right. All right, so let me simplify things just a little bit. Instead of, okay, so we have the initial case gives us 0. Then applying the recursive rule, we get 2. Applying the recursive rule again, we get 4. Applying the recursive rule again, we get 6. Applying the recursive rule again, we get 8. Applying the recursive rule again, we get 10, and so on, forever and ever and ever. So we see that S is 0, 2, 4, 6, 8, 10, 12, on and on and on forever. This is the positive evens. Or positive or 0, right? So let's say non-negative. non-negative evens. All right. So yes, this is a very silly way to define S. How would we define S without using recursion? Real simple. Right. Without using recursion, we can just use set builder notation. S is x in the natural numbers such that x is even. Oh, that's right. You guys like the Zybook uses the colon. Right. So here's a way to define S without recursion. We saw how to define S with recursion. It's that way, and that's the first example.